Good afternoon, everyone. Thanks to Telent, who was our partner who invited me to come down and speak today. So, slightly different area to what you've been listening to this afternoon already. If I can find the... Just wanted to go through some of the evolution paths in the mobile networks towards 5G, some of the things that then that changes towards getting the revenues, and what might be the impacts on you guys in the internet peering area as well as I move through it. So, if you look at anything to do with 5G, when you initially look at it, you tend to see that triangle from the ITU. Ultra-low latency communications, eMBB or enhanced mobile broadband, and then massive IoT. Massive IoT is about everything suddenly becoming enabled and on the internet for new digital services. Low latency is about using low latency systems to control stuff. eMBB is 4G but faster, fundamentally. If you look at most mobile operators, I'm conscious Neil's over there on the left-hand side, most mobile operators today are largely consumer-oriented brands. Even in the enterprise offerings, they tend to be offering groups of SIM cards with a roaming deal and very much selling to enterprises in a consumer way. There is obviously an IoT business, some more developed than others as you go around the world talking to operators. But if you look at all these new 5G vision services that you might see about connecting up factories in the Industry 4.0 area, connecting up smart cities to offer major new services there, or the obvious one of autonomous vehicles, that requires a certain amount more than what we're currently doing in 5G. If you look at most of the launches so far around the world, they're launched in the eMBB space. Now, the problem with eMBB is there's a lot of cost involved going into the network, as I'll come to in the next slide, but there's not a lot of new revenue, if at all, coming back out of the network. So the eMBB area is problematic going forward for mobile operators. So you have to start developing that area of ultra-low latency comms. You also have to develop the IoT space. And that means more than just radio. That means things like edge cloud, new security offerings, peering in the network from probably more places, more cloud connect, as you'll see as I go through the slides. So today, if you look at a 4G network, you've got a what's called an SRAN, a single RAN cabinet, out at the far end base station, usually a 1 gig microwave for many operators connecting from there back to a preaggregation site. Ratio of about 10 to 1 base stations to preags. Preags are also base stations in their own right as well. That comes from the old 2G way of doing things, and usually the early stuff was the preag was on a higher antenna mast and therefore had line of sight to the farther out base stations as you actually developed the network and made it more dense. And you also had simply a pipe, 1 gig for 4G, 10 gig from the preag back to the core, and in terms of anything else that the transmission team were asked to deliver, it was usually a frequency timing signal of about 16 parts per billion to the bottom end of the base station, the IP plug-in part, until you got 50 parts per billion coming out of the antennas, and that was fine. We go to 5G, and there's a lot of investment. So first of all, we've got to go to a new generation of massive MIMO antennas. Those antennas tend to be heavier than the old antennas, so you've got some investment in the antennas, investment in structural changes to the sites, and we've got to add a new 5G new radio card to the SRAN base station. But we've also got to go from a 1 gig to at least a 10 gig backhaul for a 5G macro cell. So that's those big three-sector things that you see on top of the roofs in London or on the towers outside of London. If you look at most of the, published trials from different operators around the world, the fully loaded 5G macros doing between 11 and 13 gigs of traffic. So you're looking at 2 times 10 gig fully loaded. Most operators are going with 10 gig from day one, with the ability to easily turn up the second 10 gig as they need it, as more devices come through. So next year, as you see the Apple 5G device come through and other 5G devices come through, you'll start to see that explosion in bandwidth. Now, you're sitting there taking this internet feed for traffic to peer from the other end of the mobile network up at the evolved packet core, and at the moment, as I said before, with the 4G world, you've probably got around 20,000 base stations per operator for the UK, each one of those putting a gig back to the network, and you've got the traffic levels that you've got at the moment. Now, suddenly we go towards hopefully over time, a large number of those base stations becoming 5G, That takes you to at least 10 gig coming back from those base stations. So suddenly those explosions in core bandwidth that we've seen over the years start to move out into the access. And a lot of the techniques that have been used in core network routing suddenly become very applicable in the access. So packet optical integration, dense 10 gig, dense 100 gig, 400 gig possibly. I heard someone mention earlier. There is an argument that from some pre-aggregation sites you could have 400 gig running back to the core. So a lot of cost. And another technology that is coming along as well is disaggregating the RAN. So this isn't just deploying into the existing sites. This is looking forward to potentially new ways of deploying the radio access network, breaking it apart between a CU, a central unit, a DU, a distributed unit, and the AAU or the RU, active antenna unit or the radio unit. What you then get is the idea that by disaggregating the baseband parts and the radio parts of the base station, you get economies of scale of putting in base stations. The kit that goes on site is smaller, less functional, therefore less cost. You also, and I think it's debatable, depends where you are in the radio environment, you get kind of a multiplying effect on those MIMO antennas because the central unit is serving more sites and able to manage spectrum and power across multiple sites. What it does mean, though, is that you now have two new interfaces in the network, the F1 and the F2, and that is based on splitting out the functions in the base station that would normally be inside the cabinet are now running over an interface. You now have to have reasonably controlled latency on the F1 and probably about 150 nanosecond based phase timing. The backhaul needs 1.5 microsecond based phase timing, so that was fairly new for the basic macro. Now you're taking it down to the next level in this disaggregated RAN. And when you go from the DU to the AAU, you're down in the region of about 10 nanoseconds worth of phase timing. So latency, number of hops, pieces of equipment you have to go through, all have an impact on that. It really is something that a lot of operators are looking at, intersecting with this whole thing around open RAN, so being able to acquire different bits from different vendors and drive down the price of radio deployment. But it also helps if you've got your own fiber or you can actually access cost-effective fiber to be able to deploy it. Another point here is that CU, certainly in many implementations, is a virtual machine. So it's a KVM or whatever virtual machine running at the edge of the network. So how far into the center of the network can you put your CU? There's been a lot of hype around putting that in the telco cloud or in the data center up in the core, maybe 2 or 3 sites for the whole country. The problem with that is you're now running the protocols on the F1, that would be PDCP, all the way up into the center of the network. And there's no mechanism of breaking into that protocol to be able to offer edge services at very low latency. So the position we've been taking is that the CU probably goes out at the pre-aggregation site, and that would also be the point where you would start running some of these low latency services at the network edge. Or if it's a private network deployment into a factory or a warehouse or something like that, it could actually run on site as well. And this is where the edge cloud starts to become very important and another key driver in 5G. So if you then look at the sort of sites where you could put the edge cloud, we've seen pre-aggregation site fairly obvious, particularly if you've got to run your services across 4G as well as 5G. So 5G at the moment is around a 4 millisecond, 2 to 5 millisecond air interface one way. 4G is still at 10 milliseconds one way. We're not going to have 5G everywhere for quite a while. So 4G, if you're going to have a wide area service, does need to be part of your story. So therefore, pre-ag enables you to balance network, fiber, and routing latency with the air interface latency to get a sub 25 milliseconds round trip. Enterprise site, actually doing stuff on customer prem, is where a lot of activity is happening already. So this is where you're finding people going in and saying, I'm going to 5G enable a factory or a port or a warehouse or something like that. And the good news about that is the risk for the operator in investing in all the new equipment is taken down a bit because the customer's actually paying for their site to be upgraded. And then the aggregation sites, so that next layer up in the network. If you think about the UK, most of the operators would have probably around 100 to 200 aggregation sites, maybe 1,000 to 2,000 pre-aggregation sites. So the aggregation site is a viable alternative to put the edge cloud, depending on the latency out to the edge, the services you're trying to run, the space you've got, etc., and how much latency you've got in your access network. So when you're out in the edge of the network, you've got some technologies you have to deal with, which in the past were dealt with for you because your services ran in the core. You always ran the services up on the SGI interface, the IP interface, anchored to what's called an APN on the internet side of the mobile packet core. And the problem with that is as you move that further out to the edge, using the standard 3GPP technology that's available to us today called CUPS, Control User Plane Separation, where the control plane stays in the telco cloud, but the user plane can move out to the edge. It's great for low mobility defined coverage area services. That enables you to do, say, a factory with the control plane in your core network and the user plane breaking out at the edge to run the machine algorithms or whatever it is in the factory to control factory robots and stuff. They don't enter and leave the building. So CUPS is fine for that, but if you need something that has got a wide area coverage, then CUPS at the edge of the network, you're still anchored to an APN. You can't hand over from one to another, and you end up with this problem of you either lose session continuity or low latency, but you can't have both. The only technology that's available to us to solve that problem today is MEC from ETSI. That's multi-access edge computing. That enables you to kind of open the GTP at the edge of the network. There are APIs in there to be able to offer lawful intercept and billing and charging at the edge of the network and transfer application state from one site to another as the devices move around. Now, this should all get fixed in about 3 to 4 years' time when Release 16 comes out and we get this thing called the UPF, the user plane function in the next-gen 5G core. In that instance, you're still anchored to the UPF, but you do have signaling to enable you to hand over. So it all comes back together again in a few years' time. Some operators are saying they won't offer wide area network edge services until the UPF is available. The danger with that is that the mobile community is no longer competing with its other operators in the country. They're competing with other technologies, and the cloud guys are all trying to get into this space as well, looking at putting edge compute in factories using other radios like Sigfox or LoRa, and then just having a lease line from the local operator back to their cloud. So it's kind of not a good idea to wait for 3 or 4 years and hope that the market's still there. So I picked the MEC example of an edge cloud rather than going through each one. They're very, very similar from an edge cloud. You get to your hub site, your preaggregation router on the backhaul. That's doing all the dense 10 gig, 100 gig packet optical and phase timing that you need. But then you break out into a mini data center at the edge of the network. You use an SDN service chaining. In our case, we've shown the Contrail system from Juniper. And we basically chain in the functions that are needed. So the first thing you need at that point in the network is an IPsec gateway to open the IPsec tunnel that protects the traffic between the base station and the core. So that opens the IPsec. In this case, a MEC server to open the GTP, and then we chain in all of the different applications. Interestingly here, there is actual breakout possible. You can have breakout applications that would connect back to the application provider. So MEC application 1 could be, I don't know, it could be the London Smart City application, or it could be the BMW factory application. They will be breaking out back to the cloud where the back end of those applications are located. So you basically have firewalling. You also have the potential for a multi-cloud environment, almost certainly multi-cloud environment. But also, you could be peering from here. I've heard operators talking about using MEC and CUPS at the edge to break out traffic and get it off to the internet exchange as quickly as possible. An example of that was last year, the UK Trans-Pennine project was basically about putting 5G along the railway line between Manchester and York. It came to a bit of a bumpy end because the government ran out of money, but at the time they wanted either end to connect to the Manchester and Leeds internet exchanges to get the traffic straight off the train and into the internet as quickly as possible. So there you go, a multi-cloud. You've got to be able to connect back to parts of this function running in the operator's cloud in the center of the network, but also the public-private cloud where the application provider's cloud applications are running as well. What does an edge data center look like? It's a small version of the data center you know and love from the core of your network. I've shown one there that shows where you have to put a cabin out at the preag site. Some operators are blessed with having lots of property at the edge of their networks, like BT. They've got all their old local exchanges. They've got their trunk exchanges as well from years ago. Other operators around Europe have just got an enlarged cabin in this part of the network, so they have to, an enlarged cabinet, sorry, they would have to build an enlarged cabin to put this stuff in place. And some are actually looking at this. So, is it real or is it just PowerPoint? Well, this is one example that we've already done. Most of the edge cloud stuff is still in trials, but one area we have done it in the UK is with the satellite applications Catapult up in Westcott in Buckinghamshire. If you look at the picture, you can tell it's an old RAF base. It's actually the place where the UK's ground-to-air missile program was tested and rolled out during the 1950s. The testbed there runs completely on Juniper. Apart from the base stations come from Airspan. The EPC is from a firm sold by Juniper, and then the Edge Cloud MEC servers, the multi-access computing servers, are run from Saguna, integrated by Juniper. So this is a place where you can go if you've got projects that you want to try these new 5G technologies, develop applications. You can actually go there and spend a bit of money with the Catapult and use it as a testbed. They've got a Spectrum license for the site that goes from a few hundred meg all the way up to about 40 gig. So that's what it looks like, which is just a rack of kit with some cables hanging out of it. So it doesn't actually look as impressive as it sounds in a diagram, but that is available now. And we've got a couple of other trials running around Europe as well. So I think my time's up, so that should be thank you. Thanks very much.
Any questions? Let's check if there's any questions. Any questions? No, you'll be out in the coffee break, won't you? So
I've actually got to head off.
Okay,
so
if
you've got any
questions,
break, but Neil Pound from Juniper's on our marketing stand. He can take any questions and get them through to me on email. But
okay,
yeah.
Thank you.
Thank you.
Thank you.